Hello, and welcome to the third video of the FP3 chapter, Integration. On the screen is not a question to solve, but just a quick question to get you thinking. What approach might you try for this integration if you were not allowed to use the result in the formula booklet? Hopefully the word that comes to mind is what we are doing today, and that is substitution. We're going to use trigonometric and/or hyperbolic functions to help us substitute into integrals that will then simplify them and make them easier to solve. So the sorts of things we're going to be looking at are these. Particularly a something plus or minus a something squared in the denominator of a fraction. The denominator with a square root and in the numerator with a square root. And all of this video boils down to, can you find the right substitution? Sometimes you'll have more than one option. When that happens, probably one of them will be much easier than the other. And sometimes there'll only be one that will work. If you're lucky, the question will give you the substitution to use. So as a quick example of how this works, back to the question that was on the starter screen. So here, there are two elements to consider when choosing a substitution. The first is, what will make your expression here simpler? And in this case, we've got a couple of things that you might think. A 1 plus something squared, well, if we do a tan, let's say tan u squared, we know that that would change into a sec squared u. And that makes our denominator a single thing rather than two terms in the expression. The other thing you might think is that if we did the same with a sinh squared u, it would give us a cosh squared u. And both of these would be reasonable starting points. The second thing to consider, however, is that when you do a substitution, you need to substitute out the dx as well. So in this top one, if I used tan u as the substitution, I would also have a dx is equal to the derivative of tan u, which is sec squared u du, and I would have to substitute that in as well. If I used this one instead, my dx would be the derivative of sinh, which is cosh u, but not cosh squared, du. And in this case, the derivative would be on the top, and the 1 plus the thing squared would be on the bottom. So if I had this on the top and this on the bottom, you can see that they would cancel out completely. If I had this on the top and this on the bottom, they would not cancel completely, and although you could probably do that, it would be a little bit more work than this one here. So as we go through, keep that in mind. What will simplify the difficult expression, but also what will I get when I differentiate my substitution? And these two things together need to make it easier. So what I'm going to do here, I'm going to use tan. So to be nice and formal about this, I would probably say let x equal tan u. And then following from that, dx is equal to sec squared u du. And if I substitute these into the expression, this integral becomes 1 over 1 plus tan squared u times sec squared u du. And most of the point of doing that is that the 1 plus tan squared u can now simplify to a sec squared u. And the sec squared u on top I can write here. And you can see this becomes just about the easiest integral you could ever imagine, which is u plus c. The final thing to remember to do, of course, is to put your substitution back into terms of x's. If I do this in blue, if x is equal to tan u, then u is equal to arc tan x. So my final line here would be arctan x plus c. And that is the answer you have on the formula sheet. Most of the rest of the video is going to be very similar, but working through a few different types of problems and therefore using different substitutions to see how they work. So in general, if you've got this expression here, then you would probably look to use the substitution we just used. X is equal to tan u, but given the general idea of an a squared here, whatever that number is there, square root that and use a tan u. So when you square this, you get a squared tan squared u, and you can factorize out the a squareds and get them outside the integral, and then do what we did on the previous screen. To have a look at the other three, let's quickly remember the identities that we can use down here. These are very useful in what we're doing in this video. Here, a number minus x squared. To simplify that, out of all of these, probably I'm going to take one of these two on the other side. 1 minus sine squared, for example, gives me a cos squared. And if I differentiate sine, I get cos. So a cos squared inside a square root and a cos on top, that will be very good. They will cancel out. So here, my substitution, anything that looks kind of like this, you will probably want to start with a sine u. Similar thinking for this one, something plus x squared. Well, we've got this one here, 1 plus tan squared equals sec squared. But when you square root that, that will just give you sec. And when you differentiate tan, you get sec squared. So they won't quite cancel out. You could probably do it, but there is more work to do there. If instead, though, you use this one here on the bottom, 1 plus sine squared gives you cos squared u, so when you square root that, you get cos on the bottom. And when you differentiate sine, you get cos on the top. So although the tan might work on this one, it will be easier if you choose something of the form a sin u. The last one, something x squared minus something squared. You could do the same argument here. You could say, oh well, if we start with a sec, then we've got sec squared minus 1 is equal to tan squared, but differentiating sec gets you all sorts of problems. If you were to try and do that, it doesn't make it very easy. Again, you might be able to do it, but what would be easier is if you've got cos squared u minus 1 giving you sin squared u inside the square root, because you know that cos differentiates to sin. And once you square root that bottom thing, you'll have stuff that cancels again. So this one, you're probably going to want x is equal to a cos u. And like I said, there will be other substitutions that will work in these, but I would suggest for each of these various forms here, these are probably your simplest, as in the ones that will give you the most cancelling when you put everything in, and then the easiest integral to actually do in terms of u. So there's an overview of the ideas. If you just want to memorize them, feel free. But hopefully you now understand why they're useful. Okay, an example here. Use an appropriate substitution. That's not giving me much help to do this. Now we've got an x squared minus a number, so that last example here, probably I'm going to want a cos. There is a clue in the question though, because they've said show that this equals this, and if my sort of re-substitution at the end gives me an r cos, probably cos is where I want to start. So there is a slight clue in the question there. So let's give this a go. Let x equal to, now I want a 9, so I'm going to use 3, so that when we square it we get a 9. 3 cos u. So then dx will equal to 3 sin u du. Then the integral 1 over square root of x squared minus 9 dx becomes the integral of 1 over the square root of x squared is 9 cos squared u minus 9, but if I bring that out of a set of brackets there, I can make that minus 1, factorizing out the 9, and that is going to be multiplied by dx, which we know is 3 sin u du. So if I simplify all of this, cos squared u minus 1, the whole point of doing this was that this will simplify to a sin squared u, and then 9 sin squared u will square root to 3 sin u. And as we had in the previous example, that simply becomes the integral of du, which of course is u plus c. And then we need to change our substitution back. So u here, first divide by 3 and then do the r cosh. And don't forget the plus c. Obviously, if they've given you the answer, just double check that your final line matches the answer in the question exactly. Okay, a quick word if there is a coefficient in front of the x squared. That doesn't match any of these that we've talked about. It doesn't match any of the ones in the formula booklet either. But a quick bit of factorizing will put this in the format you need. I.e., if you pull out a b squared, you can have a squared over b squared if you force that out of the brackets, plus x squared dx, and then of course the b squared here, you can square root that and pull it out of the integral altogether. And then of course whatever this number here is, you need to treat that as a, because this a and this a are not the same. So that was a quick side note on that. Because of the next example, we're going to have to do exactly this. So we've got an indefinite integral here. So you can see we're going to have to put some limits in towards the end, and there is this 4 here. So that's what I'm going to have to get rid of first. So I'm going to factorize that out. I won't put the limits on because it's going to take up too much space. But the idea here is that we've got the 4 there. That will give us 3 over 4 minus x squared dx. And then I can take that 4 out of the square root, and that becomes a 1 over 2, which I can even pull in front of the integration. Like so. Now, this question did not specify that we have to use a substitution, so we're allowed to use one of the standard results on the formula sheet, and this will give us arc sine x over a, where a is the square root of this number. So I'll have 1 over 2 arc sine x divided by this will be a root 3 there and a 2 here. And I should have been writing the limits each time. Got a bit of space over here, let me put them there. Then put in the limits and see what we get. So we've got arc sine of 2 times root 3 over 4 root 3. So the root 3's will cancel, and that will just be a half. And this one will be minus a half. So don't forget we're in radians here. So the arcsine of 0.5 is pi by 6. And this will be a minus pi by 6. So that will give us pi by 3, and half of that is pi by 6. And that should be our final answer. So it's worth noting that with more complicated integrations, there will be an element of problem solving, because you might not always know which substitution to use, which one's going to work, which one's going to be easier, until you just give it a go. And sometimes, yes, they will get messier before they get better. But if it keeps getting worse, messier and messier, you might need to accept defeat and go back and try something different. And that's very much a judgment. You'll have to judge for yourself how messy is too messy. So a couple of more complicated examples to finish. This is a bit more complicated because we haven't got a simple result on the formula sheet that will do this for us. So we're going to have to use substitution. There is a clue in the question though. If r sinh comes up in the answer, probably sinh is the way to go. If we check that with a bit of logic, we've got the square root of 1 plus x squared. If I put a sinh in here, 1 plus sinh squared is cosh squared. Square root of that will be cosh. And derivative of sinh is cosh, so we'll get cosh squared, which is okay because we can change that into a half plus a half cosh 2u. So yes, it looks like this is going to work if I've sort of previewed the answer in my head. So let's go for it. So we've got 1 plus sinh squared u times cosh u du. And that will be cosh squared u du. And I can integrate that by changing it into 2u. And that will be 1 over 4 because of the 2 from the half and the 2 that comes by dividing by the 2 here. Sinh of 2u plus c. Now the other reason this one's a bit more complicated is because while you might be able to see where the r sinh comes from, if I put over here when we substitute back into x's, that comes from there, but it's not quite so clear how this thing becomes this thing. And that's because we've got a 2u here rather than a u. So what we're going to do here is use the double angle formula for sinh. And sinh 2u is equal to 2 sinh u. Cosh u, which still doesn't look like this, but in order to relate this back to the thing that we know is x, this one's okay, this is x. Cosh u, we can then also use the fact that cosh u is equal to the square root of 1 plus sinh squared u. And we know sinh u, anywhere we've got a sinh u, here this can become x squared because of this, and this can become x. So here we've got 2 times x times this thing, which is the square root of 1 plus x squared. And that explains this, and the 2, of course, cancels with the 4 to give us a half. So if I was going to write that without the bits in white, I would have to make that clear for the examiner. So we've got a half r sin x plus 2 over 4 sin u square root 1 plus sin squared u and then all my sin u's there become x's. And that's quite a nice little trick. If you've got a sin 2u, do this in order to get them all back into sin u's that you can then convert back to x. Okay, a final and possibly the most complicated example here on the screen. This is more difficult obviously because of the x cubed here, but I'm still going to start with this. So to give you an idea of what would go through my head, I would do what we've done before. I would say I know that tan squared plus 1 is going to give me a sec squared. So the square root of that is going to be the square root of this, is going to be sec. And if I differentiate because of this, that would give me a sec squared on the top. So sec squared over sec. But then I would also have tan cubed here. Oh, it's not looking very nice. Possibly you could do it that way, but I think there's an easier way. So what I would then do is go back and think, what else do I know? I know that if I do sin squared plus 1, that gives me cosh squared. So if I'm square rooting this, that'll give me a cosh. And if I differentiate sin, I get cosh. So I'm going to have a cosh over cosh, but I am also going to have sin cubed there. The integral of sin cubed might not seem that great, but we have done that before by splitting it into sin and sin squared and then changing sin squared into cosh squared minus 1. So yes, this looks like it's going to work. So that would go through my head, or maybe jot down on a bit of paper to get it clear whether this is a good substitution to use. I've decided that it is, so I'm going to let x equal to 3, so that when it squares we get 9 sin u. So dx is equal to 3 cosh u du. Now granted, it hasn't said that we have to use a substitution in this question, but that's because I've taken part of the question away in order to show you that process that goes through my mind initially. What the question actually said was using a suitable hyperbolic function as a substitution, solve this. So actually the question did give us a bit of a clue that it was a hyperbolic one, so we could have ignored the tan option straight away. But I wanted to show the process that I would go through. So this then would become from 0 to 6, or actually it might also be a good idea to change those limits. Sometimes you can change back into x's at the end, but I don't think that's going to be a very easy thing to do here. So if x is equal to 6, 6 over 3 is 2, then u is equal to r sin of 2, which is not a very nice limit to have, but we'll go with it and see what happens. And if x is equal to 0, 0 over 3, r sin of 0 is 0. So I'm going to change that to r sin 2, 0. Okay, let's continue on with the substitution. 3 cubed, 27, sin cubed u over the square root of 9 sin squared u plus 9, but I'm going to factorize that out, times 3 cos u du. Okay, so we've got a 3 on the top, but we're also going to have a 3 on the bottom from the square root of the 9. Sin squared u plus 1 is cos squared u. Square rooted is cos u. So all of that is going to cancel with cos u. I'm doing some of this without actually writing it out because I've got limited space on the screen. So I can jump straight to this line here. Sin times sin squared u du. And that gives me sin u times cos squared u minus 1. Which gives me a sin u cos squared u minus sin u, which doesn't look very nice, but we have talked about on a previous video, and that integrates to 1/3 cos cubed u minus cos u from the limit 0 r sin 2. So we did the substitution. Lots of things cancelled out, which I haven't written down explicitly but talked through. That gave us the sin cubed, which we split in order to integrate using this thing in the brackets multiplied by its own derivative, that pattern that we talked about. It gives us all of this. Now at this point you can put your limits in. This one's a bit easier than this one. You could do all of that on your calculator, I guess, by doing r sin 2 and then doing cos of the answer and then doing the cube of the answer divided by 3 and so on. And that's okay, that will work if you're happy with a decimal answer. But the last thing to mention here is that if you want an exact answer, you're going to have to use the fact that this thing equals u, gives you another piece of information to use instead, a more helpful piece of information. Because if r sin 2 is equal to u, then 2 is equal to sin u. That's the same piece of information. And if 2 is equal to sin u, then cos u, which we've used the fact is equal to the square root of sin squared u plus 1, square root of sin squared u, but we know that sin u is 2, so that's 2 squared plus 1, square root of 5. So using the identity again to connect sin u with cos u, I've changed this piece of information into a more useful piece of information, which is effectively the same information, but more useful for what I'm substituting into. And this will allow me to keep an exact answer. Unless you've got a really fancy calculator that will do that for you when you substitute in this, but mine won't do that. In order to get an exact answer, I need to go through this process. So 27 times 1/3 of root 5 cubed minus root 5 minus 1/3 cos of u when u is 0, I know that that is 1, minus 1. Whew. And if I start putting that on my calculator, hopefully it will keep it nice and exact for me. Ooh, that's not a very nice number, but in the end we get 18 plus 18 root 5. And that, I hope, is the correct answer to this integral. So one more time, figure your substitution out either from clues in the question or by running through it quickly in your head as to whether it looks like it's going to work. Substitute in, simplify as much as you can to get a simpler, but not necessarily easy, a simpler integral. Do the integration, put in the limits, don't forget to substitute the correct limit, either change the limits into u or change your expression back into x's, and then simplify down your answer as much as possible. That should be enough for you to do the questions in exercise 4C. And maybe I'll see you in the next video.